And you can interact with the environment. There are up to 32 sprites on screen, which is to be expected in a modern Commodore production. And more than 1,000 sprite frames so far, but Morissette is still going at it, so expect them to grow. So it's a graphic mode that is not used very often. And the reason is that, I mean, it's very heavy on the CPU and on the memory. So, basically, when you have a bitmap screen on display, more than half of the big bank is taken by the graphics, and things get worse when you want to move the graphics around. As you know, it takes a lot of CPU time, roughly 5 times that of moving characters, and even more if you want to move the color around. From the point of view of the plus, you can have any 3 colors plus background color on screen, and you don't have any restriction imposed by the card set. So really, the screen is a canvas, and you can do whatever you want with it. So let's start to take a look at the first challenge, that of the seamless room transition. So when you are dealing with platform games and the character moves from one room to another, there's a bit of a downtime, so to say, where the next room is calculated in memory. This is historically done in a pretty possible way. You can either blank the screen, as you can see in the first example here. So the Commodore 64 can really switch the screen off, basically, and all the calculation happens in the background, and then you bring the screen up again on the new room. Or you can use a second memory buffer, like in the second game here. So the new screen is calculated in the background, and then the 2 memory buffers are, the 2 video buffers are switched. And then you don't see that flash of blackness on screen, so which is more pleasant to the eye, but it comes at the cost of memory. And then there's a third approach. This third example here is Cybernoid 2. It's done in bitmap mode, by the way, but it's tiled, as you can see. And in this case, exactly because you don't have much memory for the bitmap mode itself, let alone using 2 buffers. In this case, I mean, there's no way to put the dust under the carpet. So the composition of the screen happens, and the user just sees it. I mean, these videos are slowed down, of course, to show this even better. What would happen with the Pig Quest? As we say, we don't use tiled graphics, which means that every screen is like a bitmap. And of course, it's crunched with LZ77 cruncher, which means that it takes a long time to decode, even with the most optimized decruncher that we put together exactly for this game. And this is a simulation of what the screen would like if we were using the screen blank approach. So bearable probably, but not great. So we took another approach. We call that speculative rendering. So how does it work? When the player is moving the character around, will get close to some specific exit that leads to another room. So what we do is that we use unused CPU resources from the game logic to speculatively build the next room, the closest room, in the background. Then upon entering the room, the 2 buffers are switched and the action resumes. Now you might ask, okay, what happens if you don't enter the room? Well, nothing. Usually it's a waste of time in building the new assets. But then the character will go to another room and the process will start again. So as long as we don't slow down the action screen, this is perfectly acceptable. So seamless room transition, this happening in the background, we said, but how does it work? Because Commodore 64 doesn't have background processes or multi-threading capabilities or such, right? So this is actually the real code from the game. The way you run a game loop, you read the controls, then you draw the hero. As you can see, there's some raster time being used on the left, or the right, sorry. Then you run the artificial intelligence for the other actors on screen. You create the sprite list for them. You update the environment with bitmap animations. update the HUD. It contains things like health score and time left and the likes. And then you finally push all this information that you've calculated to the display list, right? And at this point, you should wait for the next screen to be displayed, which happens at the end of that red area there. So at this point, everything that is being calculated and put into display list is then put on screen, right? So we just use this time here. So what speculative rendering does is that it leaves some headroom first, and then passes that green area there as an input to a function that comes up with an idea of how much of the next room can be rendered using exactly the raster time. And that's exactly what it does. And you can see that upon moving to the next iteration of the loop, a little bit of the next room on the right has been computed. So run this loop many times, and by the time the character reaches the exit on the right, the room will be ready, and it will just go through. Animating large bitmap objects. This is the next challenge, and probably the toughest one. This game is done in bitmap mode again, and there are many animations to screen. You can see like the flames here, the puff of smoke coming out on the right, and there are much larger objects, but we didn't want to really spoil the game today. So yeah, but there are large bitmap objects moving on screen. In order to solve this problem, we use two approaches. The first one is called delta coding, and it's not the first time that it's used in games. And the other one is, we call it GFX as a code, and we'll see what this is about. So delta coding, let's take a look at this example. This is the animation, the smoke animation from the second thumbnail in the previous slide. This is really the way bitmap animations are done on any computer. So you have all the frames, and then you just copy them from the memory buffer to the video buffer. In this case, each frame on the Commodore 64 takes 720 bytes. So it's quite large, and there's 13 of them. So to plot to one frame with fairly optimized plotting routine, this animation will take 10,000 CPU cycles. Now, mind you, on a PAL screen, we are talking about 20,000 CPU cycles available to draw one screen. So half of the CPU time would go just to manage this animation. And, we also have to run the game, play the music, etc. So, and there are more animations in the same screen. So this will not be possible normally. Let's see what delta code does. It starts from the realization really that not every pixel in a frame changes, especially if the animations are quite smooth, like those that Moise had put together. So in this case, we transition from frame 5 to 6 of the previous animation. We see that only these pixels on the right have changed. So can we maybe store only the pixels that have changed? Yes, turns out we can do that. Of course, we don't just memorize those pixels, but also we need at some point more memory to specify where the pixel that's changed goes on screen. So some kind of RLE information, right? So let's say we double the amount of information that's needed to code a byte, but still, since there's way less than half of the bytes that change in this specific frame, the memory footprint is more than halved. And this also makes speed code possible. In fact, it makes it necessary because we don't have the luxury of just doing copy loops. We need to address the individual pixels. How does it work? So this is a regular copy routine. This is the way that regular animations are done. This is for copying 8 bytes of memory. From location X1000 to location X4000. So you have an index register. You read memory from X1000, you put it to X4000, you increment the index register, compare it to 8. So are we done? No, go back to the loop, right? Upon executing this loop, this is the result, and you have to trust me that it takes exactly 121 CPU cycles. So 121 CPU cycles just to copy 8 bytes of memory. And one frame of that animation is 720 bytes, as we say. So it's a lot. So you go to a demo coder and you ask, hey, what can I do about that? We'll say, of course, you do speed code. And they will come back with this trivial solution, but very effective one. So just read bytes one by one, take away the loop logic or minimize it. Usually this kind of block of code goes inside a larger loop. So you either take away the impact of the looping logic from your code, or you minimize it. And in this way, we took away the loop altogether. And this is 16 read or write operations, so it's 64 cycles. So not surprise here. So we almost have the CPU requirement for this copy loop at the cost of memory, of course. Is that enough? Not really, but so that's why we can do a bit better. When dealing with large objects, there will be many values that are repeated in memory, especially 0, for instance, which is like the empty pixel. So when you delete a pixel, you write it 0 somewhere, right? So we thought, let's just get rid of the source memory altogether, and the plotting code becomes the data. So the data is in the code itself. This has two advantages. The first one is that we reduce the number of load operations because we can reuse the same load operation to prepare the data for different store. And at the same time, we are using the immediate addressing code mode instead of the absolute one. So it takes only 2 cycles instead of 4 or 5. And so, yeah, it's a super gain in speed, which takes this down to 38 cycles. On average, the gain is pretty much 8x. So yeah, 8 times faster because the values are there's just a subset of them that are used. And this basically brings back to the same CPU time required to move regular car-based graphics. So this makes the bitmap animations possible. And you would ask, what's the impact on memory? Well, not so much, because after crunching, this becomes pretty much comparable, at least in this game from my analysis. Final question that I'm trying to prevent here, who the hell is going to write all this code? Of course, no one does. This is automatically generated by a Python script. So all my assets are translated into this speed code and then assembled into the game. Let's close with another, this is a classic effect. So environmental effects here, just to show that we've also done things in the classic way. So yeah, this is, each raindrop is bright, as simple as that. And also the splashes on the rain, although they interact with the screen. So you can see that the ground here is not perfectly leveled, and the raindrops just splash where they touch. It doesn't look like that, but there are only 20 drops on screen at the same time, and they are randomized, so they are shuffled horizontally, but they're carefully positioned vertically to be multiplexer friendly. So this is really just a demo effect, but it works really well, we believe, because the randomness that is used on the horizontal layer makes it look quite natural. Also, they go down at different angles, as you see, and the trajectory respects the angle. And that's the last effect that I wanted to show. This is our list of contacts, of course, in bitmap mode. So please reach out to us if you want to know a bit more, or please ask any question today.
Thank you, Antonio. Actually, thanks. I see there are some questions. There are also suggestions.
Okay.
Coming from so I don't know if that's a name or a pseudonym or nickname, Feezer Wolf. Okay. I guess the first question has been answered. It was, is this on C64? I think maybe it looks so nice that it.
Yeah, I take that as a compliment more than a question. Yes, believe it or not. Actually, if you want, we can also. I mean, yeah, I've had this question a couple of times, but yeah, it's really on C64. You can run it. I mean, yeah. So you can see it.
the rest is not really question, it's more like comments, so maybe you can, but I guess they are intended to you, so you can probably look at these in the chat box while I will, I don't see other questions coming. Yes, maybe very cool approach with your code generator. Would you like to publish it?
Yeah, sure. So I'm not new to showing stuff on GitHub. Most of my previous games are open source. So for sure, I will write this blog post about how this was done when the game is finished, and also publish the code or at least some noticeable snippets. I mean, this is massive. I mean, usually I publish the full code for things that are manageable, like my Activision ports. And I mean, there are few. Sorry, I'm very busy here playing. And they are actually short listings, right? But for this game, probably at least the outstanding parts of code I will definitely publish and share.
Okay, thanks a lot for that. I see some people are saying thanks. I'm going to leave. Please just stay a few minutes. I will now stop the recording.